Ladies and gentlemen, friends, a very good day to everybody. Thank you for inviting me for this presentation. Our topic is do it right the second time. You will have to do it a second time very painfully if you do not do it right the first time. That is me, TP Singh. We provide custom solutions to all kinds of problems related to concrete. I've had the good fortune of a very varied experience in structural engineering, geotechnical engineering, concrete technology, and material research. So this presentation seeks to sensitize the industry regarding the importance of following correct practices, doing it right the first time so that precast technology in buildings, which is relatively new, can live up to its reputation of efficiency, economy, safety, and sustainability. We're going to present a case history of a hollow core slab failure. In precast buildings, as you know, often we have these pre-stressed hollow core slabs which are erected like this, and then they are covered with concrete topping about 2 to 3 inches thick. In the building under question, these slabs were erected and the topping was installed. About 6 days after the topping was placed, one of the slabs developed this prominent mid-span crack. So immediately this slab was propped. Within a couple of days, this whole thing was dismantled and the slab brought down. So the problem was threefold. Number one, to diagnose the cause for the sudden failure. Second, to examine the soundness of the structure already built. 7 stories had been built. And third, to decide the fate of 300 slabs already produced but lying in the stockyard, waiting to be shipped. We conducted a post-mortem of the failed slab to understand and diagnose the cause. We did 2 load tests on randomly selected panels for the second part, and for the third, we conducted a test program very judiciously planned. This is the fateful slab which had cracked, brought down. The first thing we noticed was that the topping of the concrete came off quite easily, indicating a lack of bond between topping and hollow core slab, which is an essential element for the composite action. We also noticed that the webs of this slab had uncompacted concrete full of voids and honeycombs. For the post-mortem, we cut out 3 slices of the slab from the locations that you see. From each slice, we cut away these top portions in the form of prisms to be tested for compression so we can know the concrete compressive strength. The lower part was set aside for testing the bond strength between the strand and the concrete. This is how the slice looked. There was lack of compaction. We saw voids out around the strands, honeycombing, indicating lack of compaction. More of the honeycombing, and often uncompacted concrete with porosity. These are the 4 prisms that were cut away from the top part for compression testing, and 4 into 3 prisms gave an average strength of about 26 MPa as against the design strength of about 40 MPa. For the bond strength of the strands, we designed this contraption where you could measure the force required to push the strand out of the concrete, and the results were like this. Quite shockingly, in the first slice, all the 3 strands were finger push loose. In the second, the strengths were decent, about 0.6 and 1 MPa, and in the third, in fact, they were excessive because we found that the strands were rusted and so the interface was extremely rough. This is the load test being conducted on two of the randomly selected panels, complete panels. This is the arrangement of the dial gauges, and quite thankfully we found a recovery of more than 90% in almost all the dial gauges. This is how we conducted the testing at the factory. We designed our own quick load test and we designed our own criteria for failing and passing. First there was a visual examination and then the quick test. Once we started testing, just on the second day, another failure happened in the test yard with only 2/3 of the design load applied. So from then on, we decided to test every single slab. At the end of the testing, we ended up rejecting about 37 slabs from 300 lying in the factory. More observations of objectionable practices. Strand slippage is a major issue. You can see in the picture that the strand has slipped in by more than half an inch because of poor bond between the strand and the concrete. In the supervisor's sheet below, you can see several slabs being rejected of slippages. So once this issue came, we decided to visit another site, and we saw a pile which was ready for installation. And so on this table you see on top is the various slabs. On the left side you see 5 strands from the left side and then same 5 on the right side. In terms of the values, you see the yellow values are above 2, between 2 and 3 mm. The pink values are between 3 and 5 mm slippage. The brown ones are between 5 and 7, and above 7 is black. So actually all these red and blue, the red ones should definitely be rejected. The blue are borderline cases, but here is this contractor who is ready to install all of these panels up there. There's no system of testing or uh, checking. Excess oil on bed due to worn out equipment. This is the bed on which they'll be casting the hollow core slab, and they apply oil with a machine, and if you leave excess oil, you can imagine what is going to happen. The strands will get smeared with oil, and they can lead to slippages. There'll be poor bond between the concrete and the strand. Same thing. Uh, on the same project, we saw that the main structure was a steel frame which was erected 3 to 4 floors in advance, and then the hollow core slabs would be installed. So that made the installation process highly prone to accidental hits, and that was seen in several slabs. On the second picture, you see that the corner is cracked. Another one, the slab is almost ready to be covered with the topping and the corner is actually broken off. Damage in transit is yet another issue, and people do not take enough care during transit. So here is rejection happening because damage happened during transit. Stacking. Improper stacking can cause high cantilever load in the panel, in the marked panel that you see bottommost, leading to top tension in the unreinforced concrete. You see the top part of the concrete slab, hollow core slab, is unreinforced, so you cannot afford to have tension at all there. So if you have untrained personnel, these are the kind of things that can happen. Here is a stack not very properly stacked. Normally they do not stack more than 4 slabs, and someone has put 6 slabs in the stack. So if they see a pile of slabs like this with such irregular core geometry, somebody should raise an alarm. And if the team is quality conscious, they would stop production. They would, make noise that there's something wrong, terribly wrong with either the machine settings, or the concrete mix which is causing such depressions, etc. And production should stop. Latence. Latence is this paste-like material which comes out. It's actually a mixture of water and very fine paste of concrete which the cutting blade creates. So when you cut these slabs transversely, you generate a lot of this paste which keeps on lying on the surface of the slab, and if you do not clean it while it is wet, it can dry off there and actually lead to debonding. There will be no bond with the topping. So that's a serious issue, but nobody pays an attention to that. This is the kind of failure that can happen if your topping has not bonded properly with the hollow core slab. So this was the most common occurrence that was observed. Most of the webs were honeycombed and like crushed. And the single cause that was identified was a wrong setting in the machine, the extruder machine that produces these slabs. There is a finishing plate at the end. After the slab is extruded, the finishing plate finishes the top, and the wrong setting of the finishing plate was crushing the slab, and you see what you saw. Plastic shrinkage cracking in overlays, very common. People do not understand why this is there, they just accept it. But no one makes an effort to understand why this is happening and take measures to not to allow it to happen. So recommendations: do not take hollow core slab for granted. There's a great need for a greater involvement of the structural engineers with the production process and site installation. Training, of course, at various levels is an imperative. We must plan a minimum routine inspection or a test regime in the manufacturing facility, which should include visual checks like core geometry, compaction, honeycombing. Strand slippages should be measured regularly, compressive tests, strand bond tests, overlay shear adhesion tests. We must have surprise process audits by experts who are well versed with the implications of each aspect. Violations must be recorded scrupulously and remedials put in place immediately. Thank you.